Hey guys, welcome back. In this video I want to discuss about analytical derivation of kinematic equation of motion. And in this section we will make use of basic calculus and basic definition of acceleration and velocity in terms of calculus, as well as in this section you should keep in mind that this set of equations will always describe the motion in a straight line, not projectile motion. Here the straight line motion means that whenever the object moves, it always follows the straight line. For example, if the boy throws this ball from A to B and then the ball falls down to the same position at A, note that a boy throws the ball and the ball lands somewhere here. So this kind of motion is called projectile motion, and this kind of motion is the straight line. For the projectile motion, there are a set of kinematic equations that can be modified from the straight line to describe the motion. But in this section or in this video, I want to talk about the kinematic equation of motion for the straight line. And one more thing is, you should always note that this equation describes the motion with constant acceleration. Okay, which means the rate of change of acceleration with respect to time is 0. So the acceleration is always constant. So let's begin deriving the equation now. At first we need the expression for instantaneous velocity. So from the calculus definition we have that V instantaneous is change in the position of the particle upon change in the time when delta t approaches to 0, so that it gets the calculus definition, which is derivative of or change of particle position with respect to change in time, which can be equal to when this particle position xt is in terms of function of t, then we can write that dxt dt in basic definition calculus, that ft plus delta t minus ft divided by delta t when delta t appears to 0. And this is the definition of calculus. And we also know that instantaneous acceleration is given by delta v, change in the velocity of the particle with respect to change in the time when delta t, change in the time, approaches to 0. When the velocity is in terms of function of t, then we can write instantaneous acceleration as the rate of change of velocity with respect to time, and we can expand it to the general definition calculus, that it will be tt plus delta t minus ft divided by delta t when limit of delta t appears to 0. So this is the general definition of the differentiation. Now let's begin deriving the equation. Now we have first one, acceleration is equal to rate of change of velocity with respect to time, and when we cross multiply it we get, so for this is the derivative of the velocity and time. So in order to get v, we have to sum again. Actually this dv is velocity divided into very small parts, okay, and here also the time divided into many parts. So to get the overall velocity, now we have to sum again to find the whole one. So integration, if we take integration on this, then it is the another way of calling it sum. So we can take the integral from initial velocity u to v is equal to a times integral of dt from 0 to t. So from here we know that this a is taken as constant, okay, therefore we take it outside. So from here, solving this, now we will get v u v limit is equal to a t of 0 t. So it is v minus u equal to a t. So this is the equation number 1. Or you can rearrange this and make it v is equal to u plus at. Here u is the initial velocity and v is the final velocity and acceleration constant and time, okay? Because see, when time is 0, the particle velocity is initial velocity, and the particle attains velocity of v when it is time t, so it is final, okay? So this one is very important.